Hi everyone, Professor Bob Young here, and in this instructional video we're going to look at common logarithms, which we've talked about a little bit in previous videos, some more applications and modeling with these common logs, natural logarithms, and they're not called natural because they don't use makeup or anything, just a little humor there, applications and modeling with natural logs, and logarithms with other bases. All right, so for the common log, as we talked about earlier, if they don't put a base number on the log here, you must know that it is the one your calculator has, log base 10. And why I still say it's because we are 10-fingered creatures, and that's what your calculator knows for logs. So it says here, a calculator with a log key can be used to find the base 10 logarithm of any positive number. So consult your owner's manual for the keystrokes needed to find those common logs. So for example, and I think we've done this in other videos, if we took the log, and this is base 10 of course, of let's say, 10,000, your calculator should give you 4. And again, remember, common logs are base 10. And if we wanted to change this to exponential form and do the old clown face thing, and I'll just use some other colors here, we would say how to check this base number 10 raised to the 4th power equals 10,000. So just a little bit of review there. All right, now let's look at some applications here that you often see outside of class and maybe in some of your majors. So here's a chemistry problem. For you chemistry people out there, and a lot of you have to take this course, the pH of a solution is defined as pH equals minus the log of what's called the hydronium ion, H3O, with a little plus there. So it's been a while since I've done my chemistry, but anyway, where, like I said, that H3O plus is the hydronium ion concentration in moles per liter. It's starting to bring back painful memories even for me. All right, the pH value is a measure of the acidity or alkalinity of a solution. Pure water has pH 7.0. Substances with pH values greater than 7.0 are alkaline, and substances with pH values less than 7.0 are acidic. It is customary to round pH values to the nearest tenth. All right, so here's a question here. It says, with this known here, find the pH value of the hydronium ion. Well, it's equal to 2.5 times 10 to the negative 4th power. So all they're doing in this problem is just a straight substitution here. So make sure your calculators are fired up and ready to go. Now notice that they used one of the log rules to rewrite the multiplication, and this is using log rule number 1 as addition. But you don't really have to do that in order to get the answer. You could just enter this just like it looks here, minus the log on your calculator, and I'd put a parentheses there, of 2.5 times 10 caret raised to the negative 4 power and close, and it should give you this answer down here about 3.6. All right, so notice they did it using a log rule. They changed, if you remember, the multiplication to addition, and notice this base 10 number here, they're saying 10 raised to what power gives us negative 4, so that comes out of minus 4. So a couple different ways to do it and check it. Another example here, it says find the hydronium ion concentration of a solution with pH of 7.1. So in this case, we're plugging in the pH number here of 7.1. All right. Now remember, the clown face is here. If you're after the hydronium ion here, now this negative sign is a problem in front. So what we want to do is either multiply or divide both sides by negative 1 here. It's because we want to get the logarithm by itself. We want a positive logarithm here, and then we can do the clown face. Remember, if it's a common log, we'll put a little base 10 number down here to remind you, and then we will write this in exponential form. So this 10 raised to the minus 7.1 power will give you that hydronium ion which would be about 7.9 times 10 to the negative 8th power. Now, your calculator may come out with something like this. It may say 7.9 e minus 8 or something, and that's what it's talking about there. That's how they write scientific notation on your calculator screen. So watch out for that. And again, every calculator is a little bit different. You know, some of them may put a ton of zeros here. They may put 0.0000000. How many is that? 7, 1, 2, 3, 4, 5, 6, 7 zeros, and then 7, 9 to get that negative 8 power there. So it depends on your calculator. You will find out, my friends out there. All right, let's look at another thing that they use here for logarithms. It says the loudness of sounds is measured in a unit called a decibel. To measure with this unit, we first assign an intensity of I sub 0 to a very faint sound called the threshold sound. If a particular sound has intensity I, then the decibel rating of this louder sound is given by this equation. So the decibel equals 10 times the log of I divided by I sub naught. So here's just another example of how logs are used in real life. A lot of the hearing tests and stuff you get deal with logs. So again, they appear in real life all around us. Find the decibel rating of a sound with intensity 10,000 I sub naught. All right, so what we're going to do here, remember, we're going to let I equal 10,000 I sub naught, or you might want to put I-O. I-O, I-O, it's off to work we go. Stop it, young. I-O, I-O. And what happens here, when you plug that 10,000 I-O in for I, then the I-O's cancel out, and you're left with 10 times the log of 10,000. Now again, common log, that's base 10, your calculator's saying, hey, this number right here, 10 raised to what power, and we talked about this earlier, 1,000, so there is the number 4. And then 10 times 4, you have a decibel rating of 40. Now here comes what's called the natural logs, and this is huge. All right, in a previous section, we introduced the irrational number e. Do y'all remember what number e is equal to? It's about 2.71. All right, but anyway, in most practical applications of logarithms, e is used as a base. Now, e is such an important number, ladies and gentlemen, that they made a logarithm for e all by itself. So down here it says the base e of logarithm x is written this way, and it's read ln x. The expression ln x represents the exponent to which e must be raised in order to obtain x. It is called the natural log. So whenever you see this natural log ln x here, you know you got a log with base e there. It is so important, that e number, that they created a log all for it. Now let's go back to that handout that I gave you in your care package, and y'all can refer to, because all we've been talking about is properties of common logs. But let's look over here on the handout. Notice that e being a base number here, we could put the little e down here. People forget it, and we can do the clown face. The ln of the natural log of 1 is 0 because e to the 0 power is 1. Now try that on your calculators. You should have a natural log key somewhere. So if you put in the natural log of 1, your calculator will say 0. All right? The ln of the number e is 1 because e to the first power. So on these ones like this, make sure you put the little e there. And notice the properties of natural logs, I'm going to go down here, work as same as the properties of common logs. So you still got your 3 log rules down here on the bottom of this handout. Log rule 1, you can take multiplication, rewrite it as addition. You can take division, rewrite it as subtraction. And if you have the natural log of something raised to a power, you can rewrite that power in front as multiplication. So just be aware that they work the same. 1 is base 10, 1 is base e. So let's do some applications here with the natural log. And again, this appears in real life. And here's one example measuring the age of rocks. So geologists sometimes measure the age of rocks by using atomic clocks. I don't know if y'all knew that, but I think it's pretty interesting. By measuring the amount of potassium-40 and argon-40 in a rock, the age T of the specimen in years is found by this formula. So scientists over the years have developed all of these cool formulas here. And notice on the bottom there, it says where A and K are the numbers of atoms of argon, which would be A, and potassium, which on the periodic table of elements is K. And you might see that even on your vitamins, respectively, in the specimen. So here's the first example here using this formula, and you'll get some of these on your homework, and you'll get some of these on the practice test and test, but these are really just plug in and make sure you can use your calculator well and understand how to enter things. How old is a rock with A equals 0 and K greater than 0? Now, K greater than 0 means it's going to be what kind of number? It's going to be a positive number, okay? So here's the thing here. If we put 0 in for argon A, and we know K is some positive number, we're going to end up, this whole number here is going to be 8.33 times 0, which is 0. So then we've got this 1 here. So notice we end up with the natural log, or ln1, divided by this ln2 with these numbers out front. All right? Now, when you go to put this in your calculator here, this step, you might want to just do it just like it looks here. Now, on the calculator, be careful because you're going to find that ln1, remember, is the number 0 from that handout we looked at. And if you put this in your calculator right, this is what you'll end up with. The rock is new. It's a baby rock. It's 0 years old. It was just born by this formula here. All right? So I know the science instructors out there are going, but anyway, let's look at another example. The ratio A over K Hampshire is 0.212. Now, how old is this sample? See, so they gave us the ratio here of the argon to potassium, which is just a straight plug-in formula here. So make sure that y'all are doing this correctly on your calculators. Now, here's what I would do. Just like it looks, I would enter parentheses 1.26 times 10 to the 9th power. So I'm going to try to help you here as best I can. Now remember, and it's different on different calculators again, but most of them use the caret to raise to a power. Maybe yours doesn't. Now when you hit times here, be careful because you're going to want, and I'm going to go to different colors now, you're going to want to put this numerator in parentheses, see, because there's a whole bunch of stuff here. So you need to tell your calculator, separate the numerator from the denominator. So I'm going to put ln, just like it looks now, parentheses, 1 plus 8.33 times 0.212. Now you need a parentheses after the 0.212. You need a parentheses to close that. And then the last parentheses, for every open, you need a closed. And then hit divided by ln, and then your calculator, a lot of them will put parentheses on the 2. Now, maybe yours will, or maybe yours won't, but you should get this number about 1.85 billion years old. So you and your calculator must become one. You don't know how many students I've seen that they understand the problem, but they just enter it wrong, and they get the answer wrong. So you've got to practice, practice, practice on these to get good. All right, another example. You know Young likes to give you tons of examples. Where do you use this stuff in real life, Young? Modeling global temperature increase. Now, there's something that we're seeing more and more in the news. Carbon dioxide in the atmosphere traps heat from the sun. The additional solar radiation trapped by carbon dioxide is called radio forcing. It is measured in watts per square meter. Now, I don't even remember doing this in science class, but, you know, as we progress, we have to come up with some new stuff here, and boy, we better come up with a solution for this, huh? In 1896, the Swedish scientist Svante Arrhenius, now excuse me if I'm mispronouncing names out there, you history buffs, modeled radio forcing R caused additional atmospheric carbon dioxide using this logarithmic equation. So R, and they'll tell you usually what, you know, all the variables are representing here in the formula, equals K times ln, or natural log of C divided by C naught, where C naught is the pre-industrial amount of carbon dioxide, C is the current carbon dioxide level, and K is a constant that scientists came up with. It was between 10 and 16, where C equals 2 times C sub naught. Now, I know all that sounds a little confusing and so forth, but once they give us some numbers here, it shouldn't be bad. So, since C equals 2 times C sub naught, is the relationship between R and K linear or logarithmic? So, plugging in here, notice if we plug in C over C sub naught, and one of them is 2 times the other, we're going to get 2 here. So R equals K times the ln of 2, and that's going to be a linear relationship because 2 is a constant number. Now let's try another one here. The average global temperature increase T in degrees F is given by this. T in terms of R equals 1.03 R, so it wants you to write T as a function of K. So if we plug R in there for the temperature here, we're going to get 1.03 R, okay? Plugging back into our formula, we're going to get T of K equals 1.03 K times the natural log of C over C sub naught. So again, this becomes a lot of calculator problems and so forth. So it says we can use a calculator to find the values of either natural logarithms base E or common logarithms base 10. Now, did you ever wonder, Young, what if it's not base E or base 10? Let's see about that. We've got a theorem that will handle that, and this is the last thing on this video, and y'all are going to want a ton of these on the test. This is called the change of base formula, all right? So for any positive real numbers NA and base B, where A is not equal to 1 and B is not equal to 1, this is called the famous change of base formula here. So notice here, and here's how you're going to do this. They might give you the log of some base number 4, log base 4 of 7. Now, you can actually convert that both to either base 10 or base E and get the answer here. So we're going to go ahead and show you how to do this change of base formula. So on your calculator, you would just enter the log in common log terms of 7 divided by the log of 4. Or if you're a natural log person, you would put in the natural log of 7 divided by the natural log of 4. And I think I'll just do that real quick here on my calculator. I'm going to pop the calculator open. And it doesn't matter which key you use. And here's what you should get, ladies and gentlemen out there. About 1.40, 1.403, and usually they like to go 3 or 4 places. I think if they rounded it 4 places, it would be 7. All right, now don't round it on your calculator, but we want to check this. How would we check this? We could say that using the clown face here, and I'm going to extend the clown face way over, either way you did it, 4, and I hope I can reach it on my writing tablet, and this shows up on the video, 4 raised to this answer. Now, don't round this, just put the whole answer key. There's a little key that you can use to check some of these. It's called ANS on your calculator. So if you hit 4, raised to the, and you find the answer key on your calculators, many of the scientific ones have, you will get 7 back. So this famous change of base formula, man, it just blew the doors off of all logarithms now. So let's do a few more examples here, and we'll show you how it works. So let's take the log base 5 of 17. All right? So we can write that as the natural log of 17 divided by the natural log of 5. Or if you're a common log person up here, you could put the common log of 17 divided by the common log of 5. So as long as these base numbers are the same, you will get this approximate 4-digit answer here. So again, make sure you and your calculators are 1. Again, here's another example. Log base 2 of 0.1. Now they're just trying to be mean and slip you some mean numbers here. So again, you could put the common log of 0.1 divided by the common log of 2, or you could put the natural log of 0.1 on your calculator divided by the natural log of 2. Now, you know, the only way you can miss these is if you put the number where in the wrong place. I always remember that this number following the log is higher than this base number, or it's above it. So notice when you put in the numbers, if you kind of remember that little trick, you won't plug it in the wrong spot. And that's really the only way you can miss these. And again, to check it, remember, you're rounding this. This answer may go on and on forever, and they usually do. But if you took 2 raised to whatever this answer is, and don't round it, using your answer key, it should give you the 0.1 exactly back. All right. Now notice it says in previous examples, logarithms evaluated in the intermediate steps, such as the natural log of 17 and the natural log of 5, were shown to 4 decimal places. However, the final answers were obtained without rounding these intermediate values, using all of the digits obtained with the calculator. So in general, it is best to wait until the final step to round off the answer. So in other words, if you get, let's say, the log base 9 of, let's say, 97, don't go log 97 over log 9. Do not get this number and divide it by this number, or round it first. You know what I'm saying? I mean, don't round this top number because it'll throw off your answer. Do the whole thing before rounding is what it's saying there, to avoid errors. Because y'all know when people in math make mistakes, people die. All right, so let's hit that homework hard on this. Hit those common logs and natural logs. Now we have base E for our smiley clown face to work on. Bob Young signing off.